Let's see the performance tuning. This is probably the most important chapter of WebLogic. And most of the times this is what uh, gets asked in the interviews or gets focused in your work. So yeah, if you see this performance tuning, we say it's guidelines. The reason why we say guidelines is in performance tuning, there is no standard rule or thumb rule that says if you do this the performance will increase. That's why you always say it tuning. It's not, we won't say WebLogic performance improvement or WebLogic performance increasing, which means there is no guarantee that if you do what we are now studying here, the performance will increase overall. There's no such guarantee. That's why you adjust. It's like a knob. You adjust it so that you reach a point where, let's say, you have a temperature knob kind of thing, or all of you guys, the radio knob. When you are tuning the radio at a very specific frequency is when you hear that the channel. Now you adjust it, tune the frequency so that you reach that specific point in that 93.5, 93.8, the frequency point where you will be able to hear it. Now the same way here, performance tuning, you adjust it, you tune it. And these things that we're going to study today are guidelines. Means there are certain areas in WebLogic. You make sure those areas are optimized properly to achieve the best performance. Now, along with the performance tuning, we are also going to see the troubleshooting methodology. Means any problem when you come across, what's your general method of troubleshooting? Where do you start? And how do you proceed from that point onwards? That also we will see. Alright. So as we are saying, it's a trial and error methodology. In a real solution that you have, the solution spans across multiple components in a system. Let me open the zoom it. The solution spans across multiple systems, isn't it? Like the browser we have, the DNS we have. These are the routers that we always talk about. Then you have a firewall. Then you have a load balancer. Then you have Apache servers. Right? Then you have WebLogic servers. Then there is a database. Right? Then there is operating system. Then there is hardware. So when you are looking at the performance tuning, what you are essentially trying to do is you are trying to improve the response time at the browser level. So this is a browser. Let's say currently it's giving a 5 seconds response time. Means it's taking 5 seconds to load a page. Now if you are trying to say that I am trying to improve the performance of this system, what you are essentially doing is you're trying to bring it to, let's say, 4 seconds. If you can do that, it means you have improved the performance of the solution. Now obviously when you're looking at a solution, everything is involved. The DNS that you're talking here, alright? Then the routers, the series of routers you have, firewall, then the load balancer itself is involved, which sends it to the Apache servers. Apache servers have to be tuned. Then again Apache servers will send it to the WebLogics. WebLogics are again sending it to, if required, to the JDBC. Then there is operating system involved. So you need to tune at every component. But as a WebLogic administrator, you are involved in this area. the WebLogic application server tuning. Means you make certain changes to your WebLogic JVM or your WebLogic environment so that the overall time a request takes, let's say, to load the browser page here gets reduced from 5 seconds to 4 seconds or from whatever it is to a better value. So what we are trying to see here is this big green box means your WebLogic servers, how to tune it so that at a browser level you have a better response time. It's called response time, right? So that's what we are seeing, the guidelines. Now when you're looking at the guidelines, this is a stack of things that you will look at. As we are talking, you have a solution architecture. So there is a hardware involved, there is an operating system involved, there is a JVM involved. Then on the JVM, you are running a WebLogic.server Java program. That's also involved. Then GDBC, JMS. These are the various layers that are probably involved at when you're trying to tune the performance. So you may want to look at each of these layers, try to see if something can be improved in each of these layers, and then proceed with it. And most importantly, out of all these things, the most important one is always the JVM, which is this. So when somebody says performance tuning, even though all these are involved, the focus immediately goes to JVM, and that's where we're going to focus on. The next layer where you have performance tuning improvements is this. So these two layers are these two parts of WebLogic is where we're going to concentrate. So we will see what is the architecture of JVM, then how it functions, then we will see how to make it function better. The same way WebLogic server also, we will see how it receives requests, how it handles requests, how we can improve it to handle the requests in a much better way. Those are the two areas we're going to look at today. Those are the two main areas. And during this process, we will also see the troubleshooting methodology. Now before we go in there, I'll just give you a brief of a hardware and operating system. Let's look at hardware, the regular function. Usually you get a doubt that how do you decide that how many servers or how many JVMs I should put in a box? Or even before that, how do I know that my production server requires X number of JVMs? Let's say that you're working for a project or you go to a client like a bank. I say it's a bank or a Citibank. Now Citibank guys have asked you to set up the infrastructure. When they ask you to set up the infrastructure, you've agreed, okay, we will set up the infrastructure. Now how many servers or how many JVMs you need? That's the first point. Now the calculation is pretty simple. It's not as difficult as you're thinking. Now the first input you will ask from the user is, or the customer, ICICI Bank or Citibank is, what is the kind of load they are expecting? Are they expecting 1,000 users at peak time, 1 lakh users, 10 lakh users? Let's say they're expecting 1 lakh users at peak time, which means you need to design a system that can handle 1 lakh users at peak time. So you have statistics to start with. Now what you do is, you go ahead and you develop your application, right? You go ahead and you develop your application. When you are developing the application, what you do is, you start with a prototype. So you started application, let's say you have set up a very simple architecture like a browser. You won't go ahead and worry about the DNS at this point. You have a very simple, let's say a database is what you have set up, assuming it requires a database. So this is a database, alright. Then let's say we have a couple of WebLogics. or one WebLogic, for example. Then you have an application on top of it. Alright, now you are directly accessing it, the browser. You're not worried too much about the entire architecture. You're generating a prototype. So here you have an application which is deployed to WebLogic. You know that the request, they are going to require this infrastructure to handle 1 lakh users at a time. Now what you're going to do is, this infrastructure that you have, very small infrastructure, you will do load test. So you're going to perform, there is a tools, there are a lot of tools for load testing. One such tool, or the most popular tool you will see, is HP Load Runner. HP Load Runner is official or probably the best load running tool. What a load running tool does is, it simulates load. For example, let's say we take one of the scenarios in this application, logging in, or let's say a fund transfer. So the fund transfer activity can be designed in the load runner. So the load runner simulates, user logs in, does a dummy fund transfer, which will actually update a table in the database. So we are simulating a real user functionality in a load runner. Now, as it says, it's load. So that simulated activity, what we call is a test case. The test case gets executed for a large number of users. Now that large number of users, let's say we start with 1000 users. So we are starting today. So starting point, 1000 users, right, or 1K. Say it's working fine, everything going on. We let it run for about 2 or 3 hours. Then increase it to 10K, let's say. Alright. Then increase it to 20K. Increase it to 30K, like that. So you increase it to a point till it breaks. The server has to crash. Now let's say this entire test took about 24 hours. So in 24 hours you took your load from 1K to about 50K, let's say. At 50K your server broke down, which means this single WebLogic instance, can handle 50K requests. Now total requests I need this WebLogic to handle is 1 lakh. So how many servers I need? How many servers I'm going to need? One request handle 50K. 1 lakh requests, you require 2. That's correct. Or let's say, to be much more realistic, a single server handled about 10K. In that case, I will require 10 such servers. Now if I say 10 such servers, obviously I am assuming all the 10 such servers are going to be fully loaded, each one taking 10K. So my entire load is distributed. So 10K each is going to all 10 servers. So this will take, at peak load we are talking. Remember, this is not the load every day, every minute. This is the worst case scenario you're looking at. Now if you want to be much more on a safer side, along with the 10K, you will add a couple of additional servers. And normally, as JVM size, so we have decided, we started with a base model. We took how many such base models are required to handle my entire load. So now I know that I require 10 JVMs. Now let's say each JVM we started with taking 2 GB. Normally when you look at our cloud server regulars, this thing, let me start. Let me log into cloud server. WL online. Oracle middleware user project domains and code daemon pin start admin. Let's say this. We have started a server. Now this server takes 256 MB. XMS memory start, that's what we are saying. The X is related to the Java. The D that you see for other parameters is a WebLogic server parameter. Means anything that is starting with X will go to Java. Anything that is starting with D will go to WebLogic server. So let's concentrate on X things, especially these MS and MX. Memory start and memory max. That's what we are looking at, which means our admin server is going to start with 256 MB of memory. It can go up to 512 MB of memory. Now let's say the admin server takes the max memory 512. So I know each JVM here is taking 512. And when we started the prototype, we usually start for all production environments 2 GB. 2 GB is a recommended size, because what happens is if your JVM size is too big, or if you start with 10 GB JVM, means if you put XMX value to 10 GB, your operating system will have a difficulty in managing that memory. So the recommended size of JVM is 2 GB. So now the WebLogic that we have started is 2 GB in size. So with 2 GB JVM, it was able to handle 10K, and we needed 10 such JVMs. So let's calculate again. You got 2 GB WebLogic. 2 GB is where you are showing XMX value. So I need 10 such JVMs. Means the total memory that I will need is around 20 GB. 20 GB RAM is what I need. This is used RAM, means this is going to be used. So 10 JVMs. So ideally I can say you will buy a system with 20 GB RAM, put all the JVMs on it. That's one way of doing it. It'll work. But again, we have a problem like, what if the box itself goes down? So you don't want to put all your eggs into a single basket. So what you do is, the 10 JVMs that you have, you divide it into, let's say, 3 boxes. So you have box 1, box 2, box 3, like this, or box 4. Let's say 4 boxes, because you have admin also. Now you have admin here, alright. This box is holding 2. 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 So you have 8 servers handled here. Let's say you have these 2 a little high on side, 3, 3. So that will come to how many? 4, 8 plus 2, 10. Yeah. Or you can put another box. So here would have each box having 2 or 3. Now I know how much JVM. These 3 are going to take 6 GB. 6 GB is used JVM. Obviously you don't want all your system's RAM to be used, right? The general recommendation is use only half of your RAM. If I am using 6 GB and this is half, so the total memory I need to have on this system is 12 GB. Operating system is going to take 1 GB or 2 GB additional, so I'll safely put about 15 GB RAM on this system. Like that, each of my systems is having 15 GB. This is going to have 15 GB RAM. This is going to have 15 GB RAM. Like that. Now, that's the RAM part. Another constraint is the CPU. Again, the general recommendation is you should have one core per JVM. Means each JVM should be allocated to one core. Which means if I have 3 JVMs on this box, I should have 3 cores on this box. Now obviously it's not possible to have 3 cores. You have dual cores, you have hexa cores. So either you buy, you have dual cores and you have quad cores. Quad core is 4 cores. Dual core is 2 cores. Core is nothing but a CPU. If you are using a laptop, for example, let's say my current laptop that I'm using. This is all called capacity planning, guys. This is originally done at the beginning of a project. Now if you take my laptop here, let's see how many cores it has. Go to the task manager. Go to performance. So this has 2 cores. This is a dual core processor I'm running. It has 2 cores. The same way you can see the number of cores in a Unix system. Voice is low. Is it okay now? Sorry guys, I didn't see that one. Voice, is it okay now? Okay. So the number of cores on a Unix system, you can say using proc cpinfo. This is a file where you have the CPU information. You just have to cat that file. When you cat that file, it will tell you how many cores you have. You see this one, this has 2 cores. This is the cloud server we are looking at. That's a dual core processor. If it is a quad core processor, you will have 4 cores. So what we are looking at is the number of cores per box. So you will buy a box with a quad core processor. A quad core processor is quadra, so which has 4 processors or 4 processors. Let me open that file again, the image. So here, so now we know that each box requires 3 cores at least, or a quad core processor, and 15 GB RAM. That's it. Your planning is pretty much done. Those are the 2 important things that you always plan. The rest of the things are okay. Hence you can buy any hardware otherwise. Usually companies go with the vendor who gives a better package. It can be IBM servers, or it can be Oracle servers, the Sun servers, or it can be HP servers or Dell servers. Whatever it is, you can go with anybody who gives the best thing. But your primary concern is about the RAM, which you have calculated, and the processor speed. Once these 2 things you have finalized, the rest of the things are okay. You will go with money, the budget you have, the kind of service they provide, the other factors. But from a WebLogic admin's perspective, you will make sure your system has this configuration. Now it may sound pretty simple that this calculation sounds simple, but in majority of the cases you will see a lot of mistakes in this entire configuration, especially as a company or as a solution provider. Companies fail to assess the overall load that's going that the system is going to take. Disk IO, everything is considered in that load testing itself. When you are doing the load test, you are considering, you are taking it to a breaking point. But there may be certain applications with too much disk activity, so you are looking at the performance. With considerable performance, that's the WebLogic test that we did, the load testing. In that you will include that parameter also. Like, I need 5 seconds response time, so how many users I can take up. Or you can run, if your disk IO is too high, unnaturally high, then you will do another load test with a system like this. You take one system, you run a couple of servers on it, have a database, and go ahead with the load test. So you know what kind of response time you are getting. Everything you test, wherever you see something not natural, you test it. But disk IO is not something that you consider at the very beginning, unless the application is heavy IO intensive application. For a regular OLTP kind of transactions, disk IO is normally minimal. So then these are the capacity planning things. So you know how many servers you require and how many JVMs you require for your infrastructure. Now if you don't have that kind of infrastructure, or if your RAM is small on a certain box, or if your CPU power is less on a certain infrastructure or a box, you're going to see a lesser performance. So the first thing that you make sure is that you have at least your hardware is properly configured. When you look at hardware, you make sure you have enough enough cores, number of CPUs. There is at least 50% of your RAM is free. You should have enough swap space, which is a virtual memory. The /temp on your system should be enough, because this is the area where operating system writes all its rough work kind of thing. So you should have enough /temp area. For example, if you take on our cloud server, a swap space can be seen here by using the top command. This has about 3 GB of swap space. The recommendation is to have 6 GB, means double your RAM. If this is my RAM, 3 GB. Double the RAM, and 6 GB is what ideally the recommended, but we don't have 6 GB. I've included only 3 GB. So this did not meet my performance requirements. Now the second thing, temp. So if you go to /temp, again /temp we don't have it anywhere, but on a normal real system you can look at /temp space like this. Go to /temp, do a df-k on the current file system. Our /temp is actually taken from this itself. Normally you have to create another partition called /temp and assign a certain area to that one. Disk space, 10 GB, 15 GB, this is hard disk space. So you add 10. So this is used by operating systems usually. So these are the general guidelines. Out of those 4, the first 2 are the most important. The last 2 are recommended. Your systems will still work without these things, but it's recommended. These are the hardware. So when you are doing the capacity planning, you make sure these requirements are met so that you have a better system. But this is not something that you can do anything with it. Means as a WebLogic administrator, there is nothing much you can do. It's not in your hands to decide what kind of hardware you should buy. It's very rare that you will be asked, because the architect decide at their level. As a regular administrator, you won't get too much of a chance to decide unless you are a senior who is involved in the capacity plan. Now the next thing in the stack is what is important. We were actually trying to concentrate on these two things. Let's see. So what we are trying to see is how to tune the JVM. Let's see how to tune the JVM. This is the most important, which means the PS-EF grep for Java, what we did, is important. This is what we are trying to tune. This program and the corresponding parameters, all -x parameters. That's our concentration now. That's it. This is how we're going to proceed with it. We will see the architecture of JVM first, how it functions. Then we will see what is that out of this architecture that we can tune. In that process, we will see what are threads and what's a thread dump. We'll see what is a heap and what's a heap dump. What is garbage collection? How do you enable the garbage collection log? Right? And how it looks like. And how do you use it, analyze it, what are the tools that we're going to use. This is the most important part of your performance tuning, guys. So you will see all these things as we proceed further. The first thing, architecture. Let's look at this. This is a overall bird's eye view architecture of any JVM. The red box that you are looking at is a chunk of RAM that was reserved by JVM. If you take the JVM that we are looking just now, admin JVM, this is. We said it started with 256 MB, which means it went to the operating system and asked for 256 MB of memory. So operating system gave that 256 MB of memory, so it started with this red chunk. And again, there's another parameter, XMX. It said 512, means it can grow up to 512. Now in a normal production environment, what you usually do is you set this XMS and XMX values to same. So for example, I say XMS and XMX are 512. So let's say I'm going to kill this process. This is the first performance tuning recommendation. You set your XMS and XMX values to same, means you will start your JVM with the maximum required memory at the beginning itself. You don't acquire the memory in between. Now how that will improve the performance? It improves the performance because everything that's required is available at the beginning itself. You're not wasting your time to acquire the additional memory from 256 to 512 while serving the end user request. You're getting everything at the beginning. So I've killed that process. Now how do I change these values? These values are available in set domain env. So let me go to the domains, this thing, students WL online. So my first performance tuning recommendation, set your XMS and XMX to the maximum required value. Let's say you have decided that you will require 2048 MB per JVM, set it here. If you decided that 1024 is what you're going to have, set it here. If you say 512, set it here. A recommended value for all production is 2048. But for here, let's say we don't have, because we don't have enough RAM, I'm going to set it up for 512, let's say. So I'm opening that set domain env file. Alright, in here you have user or memargs, memory arguments, mem_arg, search for it. See, these are all memargs, memory arguments. You have for 64-bit you have for 32-bit. You're going to change these values. Now if you see here, so this one, if Java vendor is Sun, this is where you're going to change it. For Sun JDK, and if it is 32-bit, which is ours, these are the values. So we're going to change these values. So I'll change this one from 256 to 512 and start the server. So this is 256. I'm going to change it to 512. This is 32-bit. Right? Save it, close it. So I've set my XMS and XMX to be same. That's my first performance recommendation. Once that is set, start your server. Now grab for that process. You see now, this is 512 MB, 512 MB. My JVM has started with the max required memory at the beginning itself. It's not going to waste any time after it started to acquire any additional memory. Everything it needs is already available. Now the 512 was taken from the operating system. Now when it takes it from the operating system, the red box is what you are seeing. That's a 512 MB. That's your JVM. Now why we are starting this JVM? Because we want to run the metric application or the banking application that we deployed to it. So how JVM runs the banking application? A request will come to the JVM. JVM internally has what is called threads. That's a Java program. Java program, all of you know, it's called a thread-based program. What it means is, let's say you have 100 lines of code you want to execute. Java, when you are writing a program, it tries to allocate threads to this 100 lines of code. It also decides out of these 100 lines of codes which can be parallelly executed. Means out of 100, let's say you have 10 blocks, 10 lines of code which is independent of other 90. Another 10 lines of code which is independent of other 9. Means the 10 lines of code can be executed independently and then the result can be combined to the next one. So the 10 lines of code gets executed using what is called a thread. Think of threads like somebody who is a worker. He is the guy in the JVM or in your WebLogic server who is running the code. So what threads have here essentially is they're running the code. Code running in any Java program is nothing but executing what is called method. Where methods are coming from? They're defined in classes. We know WebLogic or Java program is a big bunch of classes. On these classes we execute methods. Who is executing the method? The thread. Now when the thread is executing the method, it is creating what is called an object. The blue circle that you are looking at, the ovals, these are objects. So when you are running a WebLogic server, all that you are doing is the code is deployed to WebLogic. A request falls in onto the managed server, let's say. Depending on the request means depending on the URL. Depending on the URL, a thread kicks in. All the threads execute methods. When the threads are executing methods, they create objects. And where do they create the objects? In the JVM. This is a JVM. So the JVM architecture, if you see, is a large chunk of RAM, 512 MB, that you have given using XMX value, which has large bunch of objects. Where these objects are coming from? They are coming from the methods that are executed by the threads. Method execution is nothing. Let's say you are transferring funds. You write a simple logic like if balance is greater than the amount you want to transfer, then initiate the transfer. That's your logic you have written. And you write that logic. Now the if condition has to be validated. Then the balance has to be stored in an object which you have probably defined as an integer. Amount, again, let's say you have defined as a float. So that takes a small object. So objects, they get created depending on the code you have written. So the threads are the ones that are creating the objects when they are executing the methods. So this is a simple logic that you're going to remember. Java code is nothing but, or a request serving is nothing but executing methods. Who is executing the methods? The threads. And they execute the methods. This red chunk gets filled with what are called objects. Now when they finish executing the threads, or the threads when they finish executing the method, what means, or let me rephrase it. When the thread finishes executing the method, it won't remove the object. It will just leave it in the JVM. But what the thread will do before leaving is, it will remove all the references to this thread, to this object. If all the references to an object are removed, it means this object is not being used by any of these threads. So this is an object in the JVM that is lying there useless. It's usually called a dead object. So threads are the ones that create the objects. When they finish, they remove the references to the objects. If they remove all the references to an object, the object itself is called a dead object, which is consuming a JVM memory. You can remove that object, take back the memory that it was consuming. Right? We'll come there. So we are looking at the big chunk which has a lot of objects created by threads. Some of these objects are currently being used by threads. Some of them are not being used anymore. They were used at some time. Now they are not being used, which means the references to these objects were removed by these threads. The objects are called dead objects. Alright? So now you have a JVM while it is running has a lot of dead objects getting created. Now when these dead objects created, we know the dead objects are going to take memory. Eventually, if everything in the JVM is dead objects, here, these blue objects, let's say, some of them are dead. So as you run your WebLogic after some time, 1 hour, 2 hours, 3 hours, the dead objects will increase it to certain level that there is no more memory left to create new objects. When there is no more memory to create new objects, we're going to have a problem. Ideally, it says no memory. That's when you will see the out of memory errors. Now to avoid that, what we say is, we have dead objects, why not reclaim the memory used by them? So the JVM internally runs what is called a garbage collector. Garbage collector basically cleans up all the dead objects, releases the memory so that the threads can create fresh objects. So this is a general functionality of a JVM. There are threads, there is a large chunk of memory, the threads create objects in that large chunk of memory. When they fill up, the chunk fills up, a garbage collector comes in, creates or removes all the dead objects, accommodates some additional space. So this process is going on. Now when the garbage collector is working, what it does is it scans through all these objects. Obviously when it is scanning, it will stop all the threads. So when GC is happening, none of the threads are functioning. So your application is basically stopped. while the GC goes through this entire 512 MB chunk that you given. Now the threads are actually working. They're all stopped, means the user requests are stopped. So GC is not something that is good for a JVM, but it's a necessity. That's what you call, you don't like it, still you need to have it. You don't like GC because when it comes, it's stopping the threads. But you want GC to come because if it is not coming, you're not able to clean up the memory. So GC is something that you don't want. Even it comes, you want it to go as early as possible. Means finish the job as early as possible and go, so that your threads can continue to work. So anytime if they have a heavy garbage collection, your application performance degrades. So this is what we're looking at. GC thread, it scans through the entire JVM to find the dead objects. While it is searching for the dead objects, all the threads will be paused. If the threads are paused, it means the end user requests are not being served, they are on a standby. So you don't want the garbage collection to come again and again and again into your JVM. When it comes, you want to finish its job quickly and then move on. Now at the beginning, the 512 MB of the chunk that you have given, means we're talking something at the beginning of the JVM architecture. JVM was invented, this garbage collection technique was invented somewhere in 1956 or 60s. That's a very old concept. It was invented in Lisp. Lisp is a programming language. I'm not sure how many of you have studied Lisp or at least know about Lisp. If you are a computer science graduate, you will see it in artificial intelligence. That is one of the topics or subjects in, I think, 4.1 of your BTech. Artificial intelligence will talk about Lisp. So here, Lisp was somewhere in 1956 or 60s we are talking about. So the JVM concept was introduced at that point. Means you take a chunk of memory, you create objects in that chunk. When it gets filled up, you clean it up. But the problem with such a methodology is, let's say I take 2 GB. Now I am allowing these threads to create objects anywhere. When the garbage collection comes in, it goes through the entire 2 GB. And during that time, the threads are actually stopped. So what you're doing is, you're stopping the threads for the whole time when the garbage collector goes through this 2 GB. Obviously, it's degrading the performance. Then, at that point, they came up or they realized something called an infant mortality rate. This has actually changed the entire architecture of JVM, this find. This was a study done by, let's say, our guys in universities, the mathematicians or the computer. If you're a computer science professor, you keep studying, how programs behave. Now, in the program study or behavioral study of an object-oriented program like Java, when they are analyzing the behavior of the program, they realized most of the objects that are getting created are dying immediately. You see the lifetime of object. This is the lifetime of an object in milliseconds, the x-axis. The y-axis is the number of objects. So you're seeing at the beginning of the program, there is a very high number of objects. Then they eventually die. Means what they realized is that lifespan of an object is very short. Now the lifespan of object or this entire graph has been put into a technical word called, it's called a technical word infant mortality rate. What is infant mortality rate in generic words? It has nothing to do with technology, guys. The infant mortality rate. It was a word taken out of, if you see the census calculations, as means the population that we have, and then the health measures. Infant mortality rate basically is a measure of how many infants are dying within a specified time after they are born. For example, if I say 15% is the infant mortality rate for India, what it means is out of 100 babies that are born, 15 are dying, let's say within the first 1 month. So my infant mortality rate for India is 15%. Let's say in a country like US, a developed country like US, infant mortality rate is 2%. Let's say. What does that mean? Out of 100 babies that are born, 2 babies or infants are dying within 1 month. Now, why is that parameter important? Because babies obviously uh, uh, die because of whatever reasons. But one important reason why many infants die, especially in developing countries, is because of malnutrition. They're not able to provide. The second thing is not able to provide proper health care. Your hospitals are not there. You don't have reachability. So normally, a country infant mortality rate says about the facilities that they are offering, the awareness. Now, when we go to, let's say, WHO, India, when goes to WHO, they say we are trying to improve the infrastructure, medical infrastructure in our country. So give us some loan, give us some money. This is one parameter we look at. Our current infant mortality rate is, let's say, 25%. It's too high. We want to increase the number of doctors. We want to increase the number of hospitals. We want to, all right, provide uh, more mobile medical kits. So give us money. Now that's infant mortality rate in general. Now take the same thing to a Java program. A Java program infant mortality rate is 80%. What does that mean? Out of 800 objects that are getting created in this JVM, 80 objects are dying in the immediate future. What is that immediate future? Don't worry. Exact time we don't have to be really careful, worry about it. Let's say immediate future. Means 5 seconds, 10 seconds. So we know that max number of objects are dying. I'm saying infant mortality rate for a Java program is 80%. Means 80 objects out of 100 are dying immediately. Most of those are local variables that in your code, looping structures, small objects that the threads create. Those objects will die in the immediate future. So 80 objects are dying out of 100. Now that was a very critical finding. Once that behavior is found, we went on and changed the JVM architecture. Earlier, we used to have what is called a long one chunk. Now what we did was we have divided the chunk into compartments. Now we are not allowing the threads to create objects anywhere they like. Leave the red part here. Let's say this is the chunk that we have. Earlier, the threads were allowed to create the objects anywhere. Now we have realized a very important property called infant mortality rate. What we are saying is 80% of the objects that are getting generated are going to be dead in the next 5 minutes, let's say. Now I know that this is a feature of a Java program. So what I do is I am not allowing my threads to create objects in any of these compartments. I don't give my threads that liberty. Instead, I'm saying all the threads should create their objects only in Eden. Eden is a very small compartment. So out of the entire 512 chunk, I'm not allowing the threads to create objects anywhere. I'm saying all new objects should be created only in this compartment. And I give out of 12, let's say about 50 MB out of 512 MB that total JVM takes. I'm giving, let's say, only 50 MB for Eden. Now when the 50 MB fills up, I know that 80% of the objects are going to die because of the nature of the object-oriented program. Now, when this compartment is full, the garbage collector comes in. When it checks here, it will find the maximum number of data objects, 80%. So I don't have to scan through the rest of that JVM or these compartments. Still, I will get the maximum data objects. So the infant mortality rate finding has actually changed the JVM sizes from a large JVM structure from a large chunk to a small individual compartments. Why we have compartments? We know that all the new objects are going to die soon because the infant mortality rate is high. So by restricting a creation of fresh objects to a specific part of the JVM in the sense, let's say only this part, Eden. Eden is a location where all the new objects get created. If that Eden is full, the garbage collector can come in. It will clean that compartment. I know that most of the objects are dead. So if the compartment size is small, obviously the GC is going to take less time to clean it up. Now it doesn't have to go through the entire space. If GC is taking less time, obviously the threads are paused for less time. If the threads are paused for less time, I don't have to compromise on the performance. So the infant mortality rate basically changes the structure of the JVM from a large chunk to compartments. And all the current JVMs are compartmentalized. And where does the new objects get created? Eden. So you have certain compartments or what are called generations of objects in JVM. Now all objects by the threads get created in Eden. Now why is it called Eden? Any idea what Eden is? Guys? What is Eden in general? Forget about JVM. Anybody who knows Eden? Eden Gardens here in Kolkata Stadium or Eden? Anybody read Bible here? Come on, none of you know Eden? Eden Garden. It's a park. Something related to Adam and Eve. That's correct. Who is Adam and Eve? That's correct. Adam and Eve. Something related to Adam and Eve. Okay, Eden is, if for those who read Bible or have knowledge of Bible. Bible says basically the world is created in 7 days. God created the world in 7 days. I had a friend who used to go to church, so I know this initial story. So God created this world in 7 days. So first day there was complete darkness, so he created light. Then blah blah blah, it goes on to 7th day, so he created the world. And then there is a park called Eden, and there are two people, Adam and Eve. And there is an apple tree in that park. There is an apple to that tree. God said, don't eat the apple. And then the story goes on like, he couldn't resist. So he ate the apple. That's where the creation started. And that's why we are here, human beings, all of us. So the point here is, Eden is the garden where the creation started. That's the name of the compartment. This is where all the creation of new objects happen. The new generation. Now once this compartment is full, the garbage collector comes in. It cleans up the 80% dead objects. The 20% it will move into what is called survivor space. Survivor space means those objects that survived will be moved into survivor space, SS1. Now obviously as add-in gets GC'd, survivor space keeps filling. Once survivor space fills up, garbage collector comes in, it removes dead objects, anything new will go to survivor space 2. Now when the next time survivor space is again, so the add-in continues to fill up, and and one more thing here, one important thing you have to remember is only one of these two survivor spaces gets used always. From add-in to survivor space 1 or from add-in to survivor space 2. If the survivor space 2 is full, garbage collector comes in, cleans up the dead object, anything that is remaining will be moved to survivor space 1. So the swapping goes back and forth for some time. 1 to 2, 2 to 1, 1 to 2, 2 to 1. Just why the reason why we want to do that is we want to leave or we want to remove the maximum dead objects. Let's say 100 objects were created in the first minute. Some of them will die in second minute, some of them third minute, some of them fourth minute, some of them fifth minute. Let's say you have 20 objects dying every 1 minute. Means by fifth minute we know that all the 100 is going to die. Or let's say 80 are going to die. Now all the 80 we want to reclaim as soon as possible. When we start with add-in, so here add-in is where they get created. Let's say about 40 objects were reclaimed there. The remaining 60 was sent to survivor space 1. Now add-in is continued to filling. So survivor space 1 has about 60. Now after 1 minute, the survivor space 1 filled, garbage collector came in, alright. It looks at the entire thing, whatever is remaining, it will clean up, move it to survivor space 2. The add-in will continue to get new objects. The threads are continue to running. If it comes for the next garbage collection, it usually goes through all your add-in and survivor space. Anything that is dead will be reclaimed. Anything that is still available will be moved into the empty survivor space. See these things, remember these things. The garbage collection will be done for these compartments at a time. This is what is called a new generation. New generation. The garbage collection for this one this is called old generation or tenured generation. So all old generation objects are especially the global variables. They are more likely to last forever. We are saying the infant mortality rate is 80%, right? So 20% of the objects are going to remain alive for a longer time. So they eventually reach the tenured generation. Before an object reaches tenured generation, we want to capture if it is dead. We don't want tenured generation to have too many dead objects, because here once it is dead, this compartment is relatively large. So if a garbage collector comes in here, it has to scan through a larger area. If it scans through a larger area, the pause is more. The threads are stand still for a more time. So we don't want the garbage collector to come into tenured generation. If an object is dead, we want to capture it in the new generation itself. So new generation garbage collection happens at a time for the 3 compartments. So it looks at add-in and the survivor space that is already full. All the dead objects reclaimed. Anything still live will be moved into the survivor space 2. And next time when the garbage collector comes in, the GC will happen on survivor space 2 and add-in. Dead will be reclaimed. Anything remaining will move to survivor space 1. In that case, SS2 is free. So at any point, only one of these two survivor spaces are in use. That's a very important thing, guys. Add-in and one of the survivor spaces is what gets garbage collected. Anything living out of the garbage collection will be moved into the empty survivor space. And these three compartments together is called new generation. So compartments is different, generation is different. Now you have a new generation, you have another one old generation. So anything that survived the garbage collection here for certain time will be moved into the tenured generation. Most likely if an object made it to tenured generation, it's very likely that it is a global variable or it's a permanent variable. And these two generations together, or these four compartments together, is called a heap. You're calling it a heap. So you have two generations or four compartments in a heap. Apart from these four compartments, there is a fifth compartment called permanent generation. What's it? Permanent generation. A permanent generation is where the actual program is loaded. The Medtech application that we deployed is actually loaded into the permanent generation. As the name itself says, it's permanent. The objects in this permanent generation are not going to die. Very rare. There will be certain dead objects. The garbage collection will also come to the permanent generation, but it's very rare. So you have all the metadata in permanent generation. That's what you call it. We also said the garbage collection. So obviously garbage collection is nothing but a piece of code, right? There are certain lines of code that's nothing but the garbage collection. Where is that code loaded? That's in the permanent generation. All the metadata of JVM, meta code of JVM is in the permanent generation. So the heap size that you are mentioning using the XMS and XMX values, that alone is not the JVM size. There is an undefined permanent generation also which should be included along with XMX. XMX is only this part, two generations only. Permanent generation you are leaving. So when you say JVM size, you should include the permanent generation also. So heap size plus permanent generation is the total JVM size. But heap size is what we define. Permanent generation is defined using another variable. This one, the max perm size. So here, how much memory your admin server is taking, if you actually look at it, it is taking the heap of max 512 plus the perm size 120. It means 512 MB plus 128 MB. It's taking 500, 600, 630 MB is what your admin server is actually consuming. That is the JVM size. A lot of people tend to think XMX is the max size your admin server is taking. It's not. XMX will tell you only about the heap. There is another generation that you are missing out, which is a permanent generation defined by a max perm size. So when you look at the overall memory consumption of a JVM, you need to consider the heap also and also the perm size. So here, these are the compartments. And what is happening here in these compartments? Objects get created in add-in. Anything that survived will be moved to survivor space 1. When add-in is full again, the garbage collector comes in again. It looks at add-in and the old survivor space. Dead objects will be reclaimed. Anything new will be moved to survivor space 2 this time. Then again, when garbage collector comes in again, garbage collector comes whenever a compartment is full or whenever a compartment is 90%. That's a threshold that we can set. It is not a periodic thing, garbage collector. Remember that one, guys. This is another misconception you have. You tend to think garbage collector comes every 5 minutes. No, garbage collector comes whenever GC will move the survivors to survivor space 1. That's correct, Kishore. So whenever the compartment is full, the garbage collector comes in. It's pretty simple. Room is dirty, come and clean it up. Don't think when it is. Compartment is full, come and clean it up. Now the tuning part comes in. The compartment is full, the garbage collector is coming too frequently. No, you can't schedule GC. You can obviously force a garbage collection, but it's an internal JVM setting. You need to tune your program so that the compartment sizes are sufficient. You don't want GC. That's the point. You don't want the garbage collection. What is garbage collector going to do if there are no dead objects? So just by bringing garbage collector, it's not going to help you anyway at all. Garbage collector should come, and when it comes, there should be dead objects. That your aim is to avoid garbage collector. But yes, if you want to forcefully garbage collector, you can do that, including using a cron job. There is a command that you can execute using WL13A. So that will do a forced garbage collection that can be done. And anything that can be done from command prompt can be put into a cron job. That can be done. But that's not something that you want. Why you don't want it is garbage collector is an internal process. The JVM will automatically invoke the garbage collector when the compartment is full. Now, as a performance tuning measure, you have to make sure when the garbage collector is coming, it finding maximum dead objects, it's able to reclaim those. So here, just summarizing your JVM thing, you have 5 compartments. These 3, then the 2. The first 3 compartments together is called new generation. The next compartment is called old generation. The next one is permanent generation. There is also another name to this new, tenured and permanent. It's called young, old and permanent. Those are 3 other names. See this one. So you got add-in, survivor space 1, survivor space 2. Add-in, survivor space 1, survivor space 2, 3 compartments together is either called young generation or new generation. It's all tenured and old generation. Permanent generation is only one. All these 5 compartments together is the JVM size. Alright. Now, the heap size out of it is new plus old is heap, which is usually defined by your XMS and XMX values. These values we have just defined in set domain env.sh under memargs. Now, this is a first performance tuning recommendation. We set it up to the same value. The next 2 recommendations are these 2. These 3 points actually summarize the entire JVM tuning. Point number 1, set your XMX and XMX to same. Point number 2, you adjust your compartment sizes. Means you adjust the size of the new generation, the first 3 compartments. You adjust the size of the tenured generation, the 4th compartment, this one. These 3 are new generation. This is tenured. You want to adjust the compartment sizes. Now, how does adjusting compartment sizes improve the performance? Let's see this. Now, your general assumption was 80% of the objects will die. That was the assumption based on which you made this entire structure. Let's say, unfortunately, your program is not following that number. Means 80% of the objects are not dying. or they are taking too long to die, which means the default compartment size. Now, okay, now before we go in any further, you said XMX is 512, means these compartments together are taking 512. And max perm size is what defines permanent size generation. So we know the size of the permanent generation. What about the sizes of add-in survivor space 1, survivor space 2 and tenured? Those will be internally calculated by the JVM. In an ideal scenario, you will have something like this. 25% or 20% of the total XMX value goes to add-in, 5% for survivor space 1, 5% for survivor space 2, 70% is tenure generation. This is a general allocation. This can be changed, but this is a normal allocation. Now the point is, we are assuming objects will die immediately in the 20%. And let's say your program is a special program. So the 20% is getting full, but the objects are not dying, which means garbage collector is coming, but it's not able to clean up anything. If it is not able to clean up anything, will the garbage collector keep quiet? It won't. It will try to come back again because it has to clean up. So the JVM keeps invoking the garbage collector again and again and again. If the garbage collector comes again and again, what will happen to your program? It will reduce. It will stop. The performance gets degraded. So now to improve the performance. Now this is the reason for application slowness most of the times. Application slow. How do you troubleshoot? Look at the garbage collection logs. Make sure the garbage collector is not coming too frequently. So what you do is, you increase the compartment size of add-in, or you increase the compartment sizes of new generation. By increasing the compartment size, what you are doing is, you are taking more time to fill up those. And your assumption is, if you take more time, probably more number of objects will die by that time. If more number of objects die by that time, when the garbage collector comes in, it will be able to clean up more number of objects. So that's your assumption, or that's your expectation. So you increase the sizes of the compartments so that you give more time to the objects, so that more number of objects will die. This will also reduce the number of GC runs. Can you guys put yourself on mute, please? Okay. So what we are trying to do is increase the compartment sizes. That's our second performance shown. Now when we do it, when our program is not performing well and we realize that it's because of too many garbage collections. Why there are too many garbage collections? The objects are not dying, or the garbage collector when it came last time could not reclaim memory, so that's coming again. Now if we don't want to come the garbage collector again, increase the compartment size. If the compartment size is more, it will take more time to fill up. Therefore, garbage collector will come late. Even when it comes up, it will be able to find more dead objects because we gave more time, so the objects will die. So that's the second way of tuning the performance. Just change the compartment sizes. Now there are certain values or parameters that you set that we will see. Compartment sizes change. The third algorithm or the third way you tune a JVM is the GC algorithm itself. All this time we are saying GC comes in, it's taken. We never really talked about whether GC is functioning efficiently or not. Means the way it is working or the algorithm that it's using to find out the dead objects and clean up the dead objects, is it efficient? We never thought about it. That's your third point. So we always say we don't want GC, but if GC comes in, make sure it finishes fast. Now the making sure it finishes fast depends on the algorithm it's using. These are called garbage collection algorithms. Now there are three types of algorithms you will see for garbage collection. A serial GC, parallel GC, concurrent mark sweep GC. Serial garbage collection, parallel garbage collection, concurrent mark sweep garbage collection. What they mean is, serial garbage collection is a single threaded. Like for example, let's say you have a room, and from time to time a sweeper comes into your room and they clean it up. The garbage collector is the sweeper and your room is the JVM. Now if a sweeper comes in, they clean it up, you cannot use that room. Means your application is standstill. So let's say the sweeper comes in, the way the sweeper cleans your room is a GC algorithm. Let's say one sweeper sweeps your room versus two sweepers sweep your room. Which is faster? Two. That's correct. So here the garbage collector comes in, it can use one thread to go through all the objects and find the dead objects, or it can use two threads to do that, or it can use multiple threads to do that. So here a serial GC is a single threaded GC. One sweeper going through all the objects, looking at each of the objects, trying to find out if it is dead or not, versus n threads doing the same check. So serial GC, parallel GC, they differ in single threaded versus multi-threaded. Now obviously if multi-thread is good, you should always use multi-threaded, right? So what's the point of using a serial threaded? The reason why you have serial thread also is, some architectures or some CPUs do not allow multiple threads. Means if you have to use a parallel GC, your CPU architecture should allow a threaded model. Now all Intel CPUs usually access it, usually allow it. There may be certain other CPUs that may not allow multi-threaded architecture, but nowadays, especially for WebLogic related activities that you're working, the CPUs are, all of them are Intel CPUs most of the times. They do support a parallel GC. Now parallel GC is multi-threaded way, so obviously we are going to use parallel 3D parallel GC wherever it is acceptable. Now look at the difference between parallel and concurrent. Now in parallel GC we are saying multi-threaded, well and good. Concurrent mark sweep GC is a type of parallel GC, but it's slight difference. What happens is, parallel GC obviously goes through the entire compartment, any compartment, with multiple threads. Now for example, let's say your garbage collecting a 10-year generation. When your garbage collecting a 10-year generation, obviously it's a big compartment. Now when this is a big compartment, your application is, your garbage collector is going to take longer time, which means your threads are going to pause for a longer time, which you don't want. There are certain applications that require a fast response, real-time response, like stock market quotes. If you see the stock application, I'm sure all of you have seen it, the price quotes change rapidly. So we cannot, if you are developing such a program, your threads cannot be on hold for a very long time. So what you do is, when you are doing a garbage collection for such an application, you don't want to hold the threads for too long. So what you do is, you finish a part of it allow the threads to run for a short time. So that what happens is the screen that you are looking at gets updated once. Then you do a garbage collection again from this point to the next point. You allow the threads to run for a minute. Then you do a garbage collection for short time. And then means instead of doing a garbage collection for the entire compartment in a single sweep, you are doing it in short pauses. Now by doing it in short pauses, what you're doing is you are allowing the application to run for a short time, then you are going back and stopping it doing garbage collection. Again, allow it for a short time, stop it. Allow it for a short time, stop it. Like that, the real-time response it is achieving, at the same time you are doing a garbage collection also. For that reason, it's called concurrent mark sweep. Concurrently, marking and sweeping happens. The marking happens along with the application itself. So concurrent mark sweep is a parallel GC, but this is usually used for applications that require real-time response, like stock market quotes. Parallel GC is used if you have a long-running heavy load applications. Long-running applications, obviously they are long-running. Now when they are long-running, you need the garbage collection to happen. So in that case, what you do is you don't take short pauses. Instead, you give a long pause to the application or to the thread, finish the entire garbage collection in one single shot, and then you allow the thread to run for a long time. So parallel GC and concurrent mark sweep GC, you decide based on what type of application it is. If your application is a stock quotes kind of application, you go for a concurrent mark sweep. Your application is slow but long running one, or it's more a heavy loaded application with long running transactions, you go with a parallel GC. If parallel GC is not supported by your CPU, you have to use the serial GC. So this algorithm itself had to be decided. Before that, the compartment sizes have to be decided. Before that, the first recommendation, you don't have to ask anyone, you directly go ahead and set it up. But these two things, they require a very in-depth analysis. Alright, so the new generation, 10-year generation, the compartment sizes, everything, they can be changed only after thorough looking at. But before that, you need to look at the garbage collection. All this time you are saying garbage collector coming, it's taking too long. So you have to know how long it's taking. Is the garbage collector the one that's causing the problem? For to understand that, what you have to do is you have to enable the garbage collection logs. By looking at the logs only, you know whether GC is coming too frequently or is the GC reason for slowness of your application. So you're going to decide, are you going to verify how frequently the garbage collector is coming? So you will enable the GC logging. A lot of people say enabling GC for this one. It's not enabling GC. You don't enable GC. GC is an internal JVM thing. Without GC, the JVM will not function. So you are not enabling or disabling GC. You are enabling simply a log file for that GC. Means you want to know what the GC is doing. By default, the JVM will not tell you about those details. You have to enable. Now, how do you enable it? You go to the same file where you set your XMS and XMX value, set domain env, and you add these values. When you add these values, the garbage collection that's happening inside the JVM will be logged to a specific log file. What's that log file? This is the log file that we are given. So I'm going to open up this file and I'm going to enable the garbage collection logging for this service. So I'm going to do it for, let's say, admin server. So I'll open the set domain env, add these three parameters. Alright. So open up the set, take a backup before you do that. So open this one, go to the end of file. At the end of the file, you have what is called Java options. This one. Alright, you're going to add your GC logging parameter to the Java options. You see, these are all Java options, -xx, -xx, -x. So we're going to add all these things here. So I'll have -verb or GC. Let me vi set domain. So I'm going to change this Java options. Comment the existing one, open a new line, add our rest of the things. You can actually remove this production mode enabled equal to false. This is not run. This is running in development mode. Let's say I convert it into production mode. Now add these values. -verb or GC. -xx plus GC timestamps. -xx plus GC details. -x log GC. Those details I'm adding. -xx plus print GC timestamps. -xx plus print GC details. -x log GC. Give a log file name. Typo error. Where is it, Dinesh? Print GC timestamps. Verb or GC -xx. Print GC details. Where is it? Just let me know. Home encode IT students WL online Oracle middleware -xx plus print ing. Okay, I'll correct it. Oracle middleware user underscore projects domains encode daemon. Let's call it gc.log. This is G. Print GC timestamps. Alright. Let's make sure this path exists. This path. Save it, close it. ls this path. No such file or directory. Say. What's our problem? Home encode IT students, or let me copy paste it. Domain home, I'm creating a gc.log. Alright. So save it, close it. Let's restart the server. Kill this. Nothing is running. Start it again. Now look at the log file that we tried to generate. This is the GC log. Let's see what's happening here. This is how a GC log looks like. I'll tell you what is happening. See this one. The first line basically tells you what is the time the GC kicked in after the server startup. Means after the server startup at 6th second it kicked in, at 7th second it kicked in again, 8th second the GC came in again, 9th second it came in, 10th second it came, 11th, 12th, because at the beginning of the server you will see too many garbage collections because there are a lot of dying happening. And when it is coming, the rest of the things basically tell you what happened. Let's say when this time at 8:58 when the garbage collection came in, it did a full garbage collection. Full garbage collection means new generation, old generation, permanent generation. All the generations is full garbage collection. You can say no, you can't start this logging dynamically. It's not possible. So garbage collection requires a restart. Any change to set domain env requires a restart. When it comes in here, let's say it came in here at 8:53, it started a full garbage collection. When it started a full garbage collection, look at these statistics. These are important. For the tenure generation, this is the size before the garbage collection. This is the size after the garbage collection. Alright? This is the total size available for new object. It means this is the total free memory in the heap after the garbage collection. So initially it was about 25 MB. After the garbage collection was done, it actually increased. If you see it, not much of a garbage collection was actually done here. It increased after the garbage collection. 28,696. It increased to a certain extent. Yes, in production it will be started at the beginning itself. Yes, you can't start things dynamically. These things have to be planned. And then if you look at this one, out of 512 MB, around 350 is free for objects. Means 150 is currently being used. And it took about 0.2 seconds to finish it. Alright. Then the new generation. If you look at the new generation, this is not new generation. Look at this one. Look at the permanent generation. This time is different. This is a different number. Look at the permanent generation. It was around 53 MB before the garbage collection. After the garbage collection is almost, it's exactly same. Means nothing was really garbage collected here in the permanent generation. It's permanent, and the total available is 53 to 48. Again, it came at 970. Before the garbage collector came in, it was this. After the garbage collection, it increased. This is the total free memory available. Look at this thing. This thing has changed this time. The new generation. New generation was initially 65 MB. After the garbage collection, it was reduced to 31 MB. The total heap available is somewhere around 510 MB this time. Permanent generation didn't change much here. 57,343 here, 57,343 again after the garbage collection. Total is also this. So at each line, it is telling you what type of garbage collection it is. Alright. How much the tenure. So before the garbage collection, after the garbage collection, still left out. Means what is the total heap size available for new object creation. Only look at this parameter. Don't look at this one. The permanent generation is not changing too much. It's increasing slowly. Earlier it was 57 here. It's 61 next, 65 next, 69 next. It's increasing till it reaches 128 because that's the max perm size we have given. Now at this point it stopped. See, it is not garbage collection happening anymore because our server is not doing anything. Now ideally you won't look at the log files like this. This is a raw data. You need some kind of tool to analyze the garbage collection logs. You will need something like a GC viewer kind of uh, tool, or something like a samurai kind of tool. So first of all, I'm going to generate a lot of log file, let's say. So I'm going to open another session. Let's generate a lot of garbage collection. We want a lot of log file. So I'm trying to deploy the application, undeploy, deploy. So some activity, you just perform some activity. It will generate GC log. User projects, domains, and code daemon bin. Let's say I have deploy.sh, undeploy.sh. First of all, list apps. This will list the applications. 4. Now I'm going to undeploy and deploy. Let's first undeploy. These are the WLST scripts. So when this is happening, ideally it should update it here something if the garbage collection is happening. Then now let's try to deploy. No garbage collection is happening. Let's hit the console. Now garbage collection is happening. If I hit the console, garbage collection is happening. So I'm going to run an infinite loop. So I'll create a small directory here. mkdir temp. Go to temp. I'll be running an infinite loop with the wget. So while true, wget console. While true will always work, means it's a ever true condition. While true, do this, wget this thing, done. No garbage collection happening. This is not good. Oops. So we want the GC to happen. Let's say I run a deploy, undeploy stuff. Do undeploy dot slash undeploy dot sh, then dot slash deploy dot sh. I'm running a simple infinite loop. It simply undeploys, deploys, undeploys, deploys. We're expecting some garbage collection log will get generated. See, something is happening. This is where we want the log. We want fast garbage collection. We can reduce the compartment size, that's one way, but this is happening pretty slowly. This is going to take a lot of time to generate a log file. Just try to reduce the size of the JVM so that we have more garbage collection. Oh, this is not getting killed. I have to kill that process. Let's kill that while loop. Grep while ps-ef grep while. The while is not running. Yeah, that's true. I can close the terminal. Yeah. Okay. Let's try to kill the Java process. Reduce the JVM size so that the garbage collection is much faster. Students, WL Online, Oracle, middleware, user project, domains, encode daemon, bin, open the set domain env, change the memogs, M-A-M-A-R-G-S. So we changed it to 512 earlier. I'm reducing it to 256, 256. It may not be sufficient sometimes. We will get out of memory in that case. We'll see. Or we can increase it to 300, let's say, for side, or somewhere around 315. Let's try with 256 first. If we see a problem with startup, then we'll. Now this is up. Or else we can do one thing, we can keep shutting down and starting up, but that will be a full GC. We want this timestamp, to be in a systematic increasing way. So now let's run the while loop. While true, do on deploy.sh, deploy.sh, done. Not much garbage collection happen. Very slow. But that's what you actually want, but we want it for our analysis purpose. Let's say that is happening. Now let's see what's the tool you use to analyze. Now for garbage collection logs analysis, you can use two logs. One is what is called GC viewer, other one is the samurai tool. Both of them are open source actually. I'm not sure if I have it on this box. Let's download GC viewer. Okay, downloading this. Right, let's open that GC viewer in the meantime. Downloads GC viewer, extract this file. So GC viewer is this. This is your GC viewer. Double click, it should open something. Here we go. This is the GC viewer. Now you want to load the file into this one. Open a file. So we need the GC log file coming up here. So let's try to get the GC log file here to this box. So this something happened here, but not too much. 94, after that 117, 141, 77. Not too much. Let's try something else. We want some activity on the admin deployment console. Log into the console. WL admin 123. Deployments. There's only one here. Okay, let's see, whatever we have, we'll try to upload it. So the GC log is what we have. I'm going to bring it to this box using WinSCP. From the Unix box to Windows box. WinSCP. Alright, connect to that box. 659.233. Code ID and code ID 123. So let's log into the GC log. Students. WL online. Oracle. Middleware. User projects. Domains. And code daemon. GC log. This one. So I'm going to get into my documents, let's say. Alright, here. So now go back to our Windows system. Open that file. This in my documents. Okay. Already have GC log. Yeah, this is a GC log. Open it up. This is what you got. Now look at this one. It took total time 5 minutes 35 seconds for the garbage collection. Throughput. This is a performance measure you will see. Means throughput is a measure that tells you basically how much time your server is spending in serving the end user requests. Now here if you see, the throughput of the admin server is 98.39%, which means let's say 98.5%. It spent 98% of its time in serving the end user requests. 98% or 98 seller, 98 10 2. So where is the 2% going on? The 2% was spent for garbage collection. So you want to maximize the throughput for a server. If the garbage collection is happening too frequently, the throughput will reduce. So you try to achieve around 95%, 96% throughput. If 96% is the throughput, 4% is the time the garbage collector is spending on the JVM is spending on the garbage collection. This is the summary. Same way if you look at memory, see this one here. Footprint is total, 246 is the total, or 256 MB is what we are actually garbage collecting. And freed memory, this is not much of a help here. Pause is important. Max pause. See this one. At max, any garbage collection was paused, means happened for a maximum of 0.6 seconds. Means there is no garbage collection that stopped the JVM for more than 0.6 seconds. So you don't want to have high value for a maximum pause, or you don't want to have average pause time too high. If average pause time is too high, it means the garbage collector is pausing your application too long. If the garbage collection pauses your application too long, your throughput comes down. Now the target throughput for a better performing application is around 96 to 97%. So you should not spend more than 3 to 4% of your JVM time in garbage collection. This is a summary, means this will give you a nice view, the right side part. On the left side again, if you see, each of these colors have a meaning and they are listed here. Let's look at the blue used heap size, and then the GC timelines. If you see, that's a green one. What we are looking at is what is the used heap after the GC. Now normally when you look at this blue line, this went up, means used heap size is increasing. The garbage collection happened here, so the used heap came down all of a sudden. Then it went on to a point when garbage collection happened again, so it came down. It went on further, the garbage collection happened, came down. So this is a general graph for any garbage collection. This is general heap usage graph you will see for any garbage collection. It will be a jigsaw like that, seesaw kind of stuff. Goes up heap usage, comes down when the garbage collection is done. Goes up heap usage, comes down when the garbage collection is done. Goes up, comes down, like that. So the heap usage will go up to a point when the garbage collector kicks in. It will collect the garbage. Now looking at this is a healthy graph for a garbage collection, means when the garbage collector is kicking, it is reclaiming the memory. Now sometimes what happens is you will see the garbage collector coming, but the heap usage will remain almost same, means the drop line you won't see. You won't see drop line. Why you didn't see a drop line? Because the garbage collector could not reclaim any memory. So the heap usage, which is a blue line, is still at the peak itself, or it stopped only at this point. So something like, let's say like this very small drops. If the very small drops are there, it means it's not able to reclaim enough memory. That's something that you don't want. You want large drops for this blue line. Large drop means a healthy garbage collection happened. The dead objects were reclaimed, so the total heap size came down significantly. Just a minute, guys. So you want the garbage collection to be healthy and the pause times to be low and the throughput of the overall system to be high. That's what you look at the garbage collection logs. If any of these things is wrong, you go ahead and change the compartment sizes so that the GC comes less frequently. Yeah, you can modify the scale. It should be there somewhere. As the graph, the content increases, the scale automatically changes. Those are adjustments here. I'm sure there are certain values, the way you can do it. Each tool has a different way of doing it. This is something that I use personally also. It gives me a quick view of what is happening with the garbage collection. I look at these two parameters: throughput, how is the throughput, and what's the average pause time. I don't want too much pause times here. It gives you a very quick glance of, okay, the GC is fine or there is something wrong with the GC. So that's your garbage collection, and obviously you don't want the garbage collector to come again and again. Now this is a JVM. If it is Sun JVM, Sun JDK versus if you are using JRocket, these are the parameters that you will be using. Alright, but the process remains same. So you have enabled the garbage collection logs and you've seen where the garbage collector is coming and reclaiming memory or not. So if you see that the garbage collector is not reclaiming memory, then obviously you want to increase the sizes of the compartments. Now this is another sample of garbage collection you are looking at. Alright, GC, 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 full GC. These are called minor garbage collections. This is a major garbage collection or full garbage collection. There is an explanation also in this document just now, the one that I've explained. So before garbage collection, after garbage collection, total memory is still available for the objects. And this is the time it took. See this one here. If you look at the amount of space available usable for Java objects without requesting more memory from the operating system. So it took total of these many seconds, 1/4 of second or something. So these are the analysis, but the analysis itself you won't do it using raw logs. You can, obviously. It's a good thing to know that just by looking at the raw logs you are able to analyze, but you always have a GC viewer to do that. Now here, if the GC is happening too frequently, you will see a couple of problems. One is the application will be slow. That's one main symptom of too much GC. So if too much GC is happening, the repercussions are like application slowness. So if somebody complains application is slow, the first thing you're going to look at is what's happening with your garbage collection. But the application slow can be for a different reason also. Application slow could be because the threads are slow. The threads may be slow for a lot of reasons. Let's say a thread is trying to write something to a disk, but the disk is slow, in which case the thread is going to take longer. Or the thread is trying to get a database connection, which it is not, so it's going to take longer. So application slowness has a lot of reasons, especially The threads are slow or there is not enough memory. Not enough memory you will be able to identify by looking at the garbage collection. So if the garbage collection is happening too frequently, threads will be slow. Let's say the garbage collection is healthy but threads are still slow. Now when you have that situation, you want to know why the threads are slow. For that one, you will take what is called a thread dump. The thread dump can be taken using a kill-3 process ID, or you can use gstack-l process ID, or you can take a thread dump from the console itself. These are three methods, or you can take it using WL13A. There are a lot of ways of taking a thread dump. Let's say if you want to take it using console, go into servers. Three methods I've talked just now. Admin server, go into monitoring, right? Then you have threads tab here, dump the threads. You're basically looking at thread stack. So you will dump the entire thread stack into a log file. You're okay guys, this is already 8 o'clock. We're okay if we continue for half an hour. I don't think we'll be able to finish it today. Okay, let's go ahead. So excellent. So you can dump the thread stack here. Now this can be done from console, or you can pretty much do it from the command prompt also. Obviously the easiest way is to do it from the command prompt. When you dump the threads, it goes to the regular console log. So let's open up a console log. So I just got out of the GC log. I'm going to open the console log, our admin.log. So I'll keep it open, admin.log, then I do a kill-3. Remember, this is kill-3, not kill-9. So here, kill-3 process ID. So I'm going to do a ps-ef grub java. Alright, kill-3, kill-3, set, and now when you did that, you see here, it dumped this entire this thing. These are all threads, and what you are getting is a snapshot of threads. Let's go to the beginning of this thread dump. Going up in the log file. This is where it was when before we started a thread. See this. This is the beginning of a thread dump. Full thread dump for a Java hotspot client virtual machine. These are the threads. This is one thread. It basically tells you the status of the thread. Alright. The name of the thread. Standby, it's waiting basically. It's an execute thread. It's basically waiting for an incoming request. Now you will see it's locking an object. Another thread. These are all threads, execute threads. These are the ones that are actually waiting for the incoming request. Apart from the execute threads, you see these are states. Apart from the execute threads, you will have other threads, internal threads of WebLogic, dynamic SSL thread. You will also see garbage collection thread. See this one, this is important. WebLogic GC monitor thread. This is the guy who is searching or monitoring the compartments. Means if the compartment is full, we are saying the garbage collector will come in. So how does the JVM know that the compartment is full? It's simple, it has a monitor. So there is a thread that keeps monitoring whether the compartment size is reached a certain value or not. If it reached, it's going to invoke a GC. So like that, you have got execute threads, you got other threads which are actually also working. These threads are also working. And DOS manager, these are internal threads. VDE replica, these are internal threads. Execute thread is what is your thread. This is basically the one that is serving your request. Now if you see this one, this thread is blocked. This is an internal thread. The muxer thread it's called. Muxer threads are the ones that will read the requests from the operating system. So all the muxer threads you will see them there, they will be kind of blocked. So this is a general thread dump that you are looking at. Now again, you won't look at a thread dump in a raw state. You need a certain tool obviously to uh, analyze this kind of thread dump. So the tool that you use to analyze, see, this also gives you a nice heap, this thing also. Ident space 67% is used, tenured is this much used, 39% is used in tenured. Right. So some of the information, it may not be useful always, but you do get certain information. Now we are interested in the state of the threads. Now what we are looking at is a snapshot of the threads. Why you are looking at a snapshot of the threads? You want to know what the thread is doing. Why you want to know what the thread is doing? Because it was getting slow. Users are complaining application is slow. Now application can be slow because of threads being slow. Threads will be slow because of two reasons. One is either the thread is working too much or something, or it is not allowed to work at all, which means the garbage collection is happening too frequently. For the garbage collection to observe, you enable the GC logs and you looked at it. Now the other part is, if the GC is good, the other part is obviously the thread is not able to do what it's expected to do. Now let's see what the threads are trying to do. So you took a snapshot of the threads. Now once you take the snapshot of the threads, you're going to upload it to some tool. So let's say we take a couple of such snapshots. I'm taking 4 or 5 snapshots. We want to compare the thread status one snapshot to other. So 3, 4, 5, 6, 7, 8, 9, 10 snapshots I've taken. So I have all the snapshots in my admin log. So everything is here. Now I need to upload this to some kind of tool. Now the tool used to analyze a thread dump, there are two tools. One is I use personally Samurai. Alright, download Samurai thread dump analysis tool. This is a GUI based tool. Recently I came across another tool called Thread Logic. I never used Thread Logic, so we'll try to use that one also. But let's first see Samurai. This is a Samurai tool. So let me download that. See the GC view logs that we used, or GC viewer, it can be actually analyzed using Samurai also. But GC viewer is a much better tool than GC this thing, the Samurai tool. So we use multiple. I just wanted to show you multiple tools. So where do I download it? Where is the download, guys? I saw the download somewhere. Where is? Oh. Okay, so you got a GNLP file here. Downloads this one. So launch it. Yeah, this is your summary tool. It's a very simple tool. Now you go to drag and drop your file or upload your file. So let's get our admin.log. This is admin.log. We want it here. So I'm getting it admin.log. I got it to our local desktop. So load that file. Admin.log. This is admin.log. Alright. I just got it from our server. So it entire uploads the log file. It detects the thread dumps automatically. When it detects, it opens up this thread dumps tab. These are the thread dumps you're looking at. You've taken 10 thread dumps, you remember? These are the 10 thread dumps and the states. And the left side, the blue lines are the threads you're looking at. These are the threads. Each of them is a thread. Right? Now at any point of time, you will know what the thread is doing. What this thread was doing in dump 1, dump 2, dump 3, dump 4, like that. Dump 5, like that. If you see this one, this thread is not doing anything pretty much. It's waiting. It's waiting on the same object. Alright. This is the object number in the hexadecimals. This is in heap you are referring to. So you have this thread. Like that, you have these are the worker threads. They basically execute incoming requests. Then you have kernel default. This is another thread that actually executes the end user request. So you can look at the thread dumps table view, this one. Now what you look out of it? We say thread dump analysis. What you look at out of it is you may look mainly for the deadlocks. So you don't want any skull symbols here. A deadlock is basically a thread is locked or it's not going to move forward. A deadlock. You're waiting for me, I'm waiting for you, so we are in a deadlock. When I ask this question, what's a deadlock? A lot of people say a deadlock is two resources waiting, two threads waiting for the same resource. That's not correct. If two threads are waiting for the same resource, one will get it first, the other one will get it next. Eventually they'll finish. A deadlock always involves a circular wait. That's a keyword. It's a circular wait. Means I wait for you, you wait for me. That's when a deadlock is. If we both are waiting for a third person, it's not a deadlock. So if two threads are waiting for a resource, it's not a deadlock. Thread 1 is waiting for a resource occupied by thread 2. The same way, thread 2 is waiting for a resource occupied by a thread 1. That's a deadlock. So you should not have any deadlocks in here. So this is a very nice, easy way of analyzing this thread dump, guys. The first thing you look at is no skull symbols. Yeah, this is perfectly fine. A second thing you will see is there are no continuous thread blocks. Except here. You see these socket muxer threads. Just now I told you the muxer threads are internal threads. They're always blocked. So you will see these three things in red. That's fine. What you don't want is anywhere else. You don't want to see continuous blocking. A red mark here and there is okay. Means a thread was blocked when you did a kill -3, but immediately it was released in the next dump. It went to green. So what you are looking at is, you should not have continuous red blocks. These are the two things you will see. So you will see if there are any deadlocks or if there are any blocking threads which are in red. Now if there is any blocking thread, let's say something here you are seeing, this one is completely blocked, the first one. So you go in there, you try to see what it is doing. It will basically tell you what it is doing here. Your Java stack is called a stack. So the Java stack will tell you what object it's waiting on, what thread it's waiting on, like that. So you will be able to analyze it further. Now thread dump analysis is usually not a job of an administrator, but we are going in depth because we want to understand how things are done. Because even if you understand from this point onwards, even if you understand something, you won't be able to do it, because this is all objects method stuff. Method is inside the code, which is only known to a developer. So we won't be able to do much here even after this analysis. But we do a basic analysis saying if there are any locks, or if there are any deadlocks, if there are any blocking threads, or if there are any circular waits, or if there are any stuck threads. Some threads get stuck. A stuck thread is something that's running for more than 600 seconds. That's called a stuck thread. Alright, so here you don't want to have a stuck thread. So then when you have a stuck thread, what you're going to do and how to analyze the code that caused the stuck thread, that will be taken care by the developer. But usually if you have stuck threads, your application will be slow. So this is a thread dump. So you know about garbage collection logs. You analyze the garbage collection logs to see why the garbage collection is happening so frequent. This all happens for application slowness, guys. We are talking about performance tuning, which is closely related with application slowness. Your performance is degraded basically, and that's when you say application is slow. Now when you are doing this one, you might come across sometimes what are called out of memory errors. Now you have given here 512 MB of heap size here, or 256 MB. Now sometimes it's possible that this is not sufficient. If it is not sufficient, obviously you're going to get out of memory error. Now in that case, your solution is obviously to increase this one, because you said it's not sufficient. That's why usually you will, in a real-time environment, you have anywhere between, you will have 2048 MB, 2 GB that is, or 3 GB, and you will increase the number of JVMs to spread your load. But even with limited load, it's possible that sometimes you're still out of memory errors. That's because of the bugs in the code. What happens is, if you have bugs in the code, ideally a thread which is creating an object here, let's say go back to the threads here, a thread is creating an object. When the thread finishes its code, it should remove the reference to the object. But because of bad code writing practices, it is possible that the thread will not remove the reference even after it finished its job. Which means there is an object in the JVM which is consuming memory. It is not being used by the thread, but it still has a reference. Because of this, when a garbage collector comes in, the garbage collector thinks that this object is still in use, so it won't remove it. But actually it is not being used, which means it's going to stay in that JVM forever, and it can never be removed by a garbage collector. Now, if such objects exist in a JVM, After some time of running your programs, 2 hours, 3 hours, 4 hours, 5 hours, all such objects will permanently consume the memory, so the compartments will eventually fill up and the garbage collector cannot remove those objects because they are being referred. So this is because of a problem with bad coding practices. So if your code is written wrongly, there is a possibility that the JVM will go out of memory. Now this leaving of the object even after the thread has finished is called a memory leak. So what you are doing is you are leaking the memory by not removing the references. If you don't remove the reference, if the thread is not removing the reference, the garbage collector cannot clean it. If the garbage collector cannot clean it, it's going to stay in the JVM, and if many such objects stay in the JVM will fill up and eventually it will say it's out of memory. So out of memory could be either because genuinely out of memory or because of a memory leak. If it is genuinely out of memory, you simply increase the XMX value. If it is a memory leak, you need to identify it. So how do you identify a memory leak? The first thing to do it is obviously you increase the XMX value to 2 GB or 3 GB. Even after increasing, if you are still getting a out of memory, because let's say 1 GB XMX took 2 hours to fill. After 2 hours you got out of memory. You increased it to 2 GB. Ideally, if everything is good, 2 GB should be sufficient because you have doubled the memory. But even in 2 GB, if you get out of memory, but this time you got it after 2 or 3 hours, which means it's an indication that it's taking longer to give you that out of memory error. It's possible that there is a memory leak. If there is a memory leak, you want to analyze what is called the heap dump. The chunk of red box that you are looking at, you want to see what objects are available in that JVM at the point of out of memory. So when you get out of memory, you take a heap dump. And how do you take a heap dump? This is a command to take a heap dump. Jmap -heap :format equal to binary. So that will generate your Jmap is again in your Java home bin. So you take Jmap, set the environment. So which Jmap? It's in Java home bin. So Jmap -heap equal to binary process ID. So Jmap -heap :format is binary. Process ID is this one. Now this will generate a file called heap.bin. This is called a heap dump. So what you are essentially doing is you are dumping the entire JVM objects into a file called heap.bin. That's what you're doing. Alright. Now once you generated it, you actually have to analyze it. It's not your job to analyze a heap dump because it's related to code. So usually as an administrator, you give it to a developer. The developers will use their own tools. The heap analysis tool is called HAT tool, heap analysis tool. We don't usually use it, but you can, if you're interested, you can download it and actually see a HAT tool. There are a lot of YouTube videos. Just go through one or two YouTube videos. It'll give you an idea of what it's pretty simple thing. What a developer basically does is they upload this heap.bin into a tool like the one we have used, either a GCView or a summary tool. It's called HAT tool, heap analysis tool. The HAT tool analyzes the objects in the bin file and it gives you the possible memory leak suspects. Means it tells you these are looking like they are existing for a very long time, but no threads are referring to those objects, because when a thread refers to object, it updates the timestamps. So the tool will simply look at each object, looks at certain properties of the object and says, okay, this is a possibility that it's a memory leak. For example, let's say an object was not referred in the last 10-15 minutes or 1 hour, 2 hours. It's not possible, right? In a regular program, an object not being referred for 2 hours, there's something wrong with it. So it will just tell you that it's a leak suspect. Then the developer will be able to see which method is creating that object. Once the developer knows which method is creating the object, they can go into the code, make the corresponding corrections, then give the code to us again, and we deploy it and see if the same out of memory problem is happening. So if there are memory leaks, the way to identify a memory leak is by taking a heap dump and analyzing it. And a memory leak usually causes out of memory error. So when you have out of memory error, what you do? You take a heap dump. Or you, first of all, whenever you see out of memory error, you increase the heap size, XMX value. You wait for some time. If you still get out of memory, there is a possibility that there is a memory leak. What's a memory leak? A thread finishes its job but does not remove the references. Now, to identify a memory leak, basically you increase the heap size. If you still get out of memory, it's a possibility memory leak. How do you fix a memory leak? You don't fix it as an admin. It's a developer who fixes it. What you do from your side is you take a heap dump. You use a gmap command. You generate a heap.bin file, give it to the developer, and the tool the developer uses is heap analysis tool. HAT tool it's called. The heap analysis tool, I think there are a couple of let me show you a document. No, I think I have it somewhere. It's Eclipse HAT tool. Eclipse heap analysis plugin for Eclipse. Eclipse memory analyzer. Yeah, you can say this is also. Just a minute, guys. Is there a where we can take a dump in heap dump? I'm not really sure. Heap dump on heap. Jmap is there, right? Jmap is a Java command. You don't have anything to do with Windows. So you have Java home bin and you will have Jmap command. It's the same command. Exactly same command. It does not change. Thread dump, you might have a problem because you don't have kill-3. In that case, you have to use jstack, the one that I have given. That's again, jstack is again a Java command. So you have a Java home bin. So in the Java home bin, you will have both these commands. So both thread dump and heap dump you can take in Windows using the same commands. Kill-3 you can't use in Windows. Now this is a memory analyzer, guys, HAT tool. It basically gives a nice pictorial view of the leak suspects and everything. They upload the heap.bin into this tool and it gives you that. So now that you have generated a heap dump, it will take a little time. So heap dump is created here. So you have a heap.bin file. This bin file you upload it to a server, alright, your desktop, and then if you download it, let's say we download the latest one, say if it happens quickly. Blah blah blah. Thank you for downloading Eclipse. It's very slow. Okay, so basically that's more of a developer's work. Probably you can have a look at it and if you are really interested in that. So you just download it and take the heap.bin file and do it just the way we did it for GC Viewer and Summary. Alright, let's move on. Now the analysis of dump. For the thread dump you are using Summary. For GC logs view also you can use Summary, or we have used another tool, GC Viewer here. For heap dump we don't analyze the heap dump as an administrator, but we can always be interested. You take a heap dump using jmap command, you analyze it using the memory analysis tool or a heap analysis tool. That's also an open source tool. You just upload a heap.bin. Now what you are going to tune, okay, now I think that's the tuning part of JVM. Now before we go any further, let me summarize everything. So what we're going to tune and what's the problems you're going to come across and your troubleshooting methodology. Those are two things. The tuning things, you're going to tune the overall heap size, or you're going to tune the compartment sizes, or you will tune the GC algorithm. These are three things you will tune. Heap size you are changing here. Compartment sizes, you will change these parameters, -xx new size. When you set the xx new size, the tenured size automatically comes in because the overall xmx you are setting. So xmx minus new size is tenured size. Then you are setting up the perm generation again using the perm gen and max perm gen. This is not perm gen, this is perm size and max perm size. So this is wrong here. So by adjusting the compartment sizes, you can give more time to the garbage collector. So when it comes, it will be able to clean up more. That's one tuning. The second level of tuning that you do is serial GC, parallel GC, concurrent mark sweep GC. You can again set those parameters using your XMX and XMX. So like this -XX, right? Use serial GC. That's how you use serial GC. Use serial GC. If you want to use parallel GC, you're going to say use parallel GC. The same way, if you want to use concurrent mark sweep GC, you're going to set a parameter, use concurrent mark sweep GC. This is how you define a garbage collection algorithm. Now your confusion comes especially in these two, whether you want to use parallel GC or concurrent mark sweep GC. It is especially for real-time applications, means real response required application versus long-running transaction application. I gave you a couple of examples also. The example for concurrent mark sweep is stock quotes. That's the best example. Anything that that requires frequent recalculation and refreshing. Whereas a parallel GC is a long-running transaction, like a lot of database related queries, mining related report generations. That kind of applications will require parallel GC. Alright, these are the areas and the way you tune it. And also we talked about when you have a problem, what you do. So when you have a problem, the first thing, troubleshooting always starts with console, with log file, right, guys? So let's say if I have to troubleshoot anything, this is the troubleshooting technique you will always use. Methodology, it's more of, I think I should put it in the PPT itself. The first thing you look at is you look at the log files. Now if you find something related, some error you need to get. See, you cannot troubleshoot without errors. You cannot troubleshoot without log files. That's not possible. Now if the log file is not showing anything, you might go one step further and you can enable debug. How do you enable debug? Is basically you add a parameter, add -verbose parameter to Java options. So here, let me go back and add it to our server. Our current log level is information. Now what we are trying to do is set it to debug. Now why we are trying to set it to debug is we want more information in the log. The current log is not showing anything, but the user is complaining there is a problem. So what I'm going to do is I'm going to add verbose. The verbose will make log file to dump individual at debug level. So I'm going to kill the existing server, run it again, start at tailfnf admin.log. So now you see this log file. This log tells me everything that the server is doing. Earlier it wasn't. Earlier it was telling only limited things. Now it is telling everything that the server is doing. So sorry guys, that's my son. Just give me a moment please. Okay, sorry about that. So here, where are we? Just so my log is showing much more information than regularly it would. So now I will be able to see if now normally when a user complains that I'm getting a problem, so if you don't see anything in the logs, the next thing you will do is you enable the log file debug mode. You ask the user to perform the activity again. Now why you want to do that? When the user is performing the activity which has a problem, you want to see what is happening in the server. So you enable the debug mode. You basically see what the user is trying to do, what the server is trying to do when it is happening. You will be able to see if there are any problems. It's very likely that you will find the problem here itself. Apart from that, let's say you are still troubleshooting. Alright, so this is the second step. The third step, you will take a thread dump. Whenever a user is complaining application slow, you want to, let's say, take a thread dump, see what the threads are doing, what methods they are executing. You will be able to find out certain clues. Then you take a heap dump. Right? Try to see what the problem is. Then you look at the garbage collection logs, especially application slowness related issues. So these are the 5 standard steps used for any troubleshooting, guys. Any troubleshooting. There's no chance that you will not be able to troubleshoot a problem with with these five things. If you still have a problem, it's very likely that there is a bug in the product itself. Most of the times you will be able to troubleshoot the problem with the thread dumps, but you need to have a very strong development team if there is a problem with the code. This is all analysis. You are analyzing. You're not giving a solution. You can't guarantee that. If there is a problem, let's say there is a memory leak, all that you can do is you take a heap dump, you identify that there is a memory leak. You can't go beyond and fix the code yourself. So this is a process for analyzing. This is a process for detecting a problem. The solution has to come from various other teams also apart from us. So what we can do is you can tune the performance, you can make sure the garbage collection is not happening too frequently, but the code itself is buggy, the garbage collection will come. You can't stop it. So you need to tune those areas slowly. But these are the areas that are definitely, this is an exhaustive list of areas, an exhaustive list of techniques that you use to troubleshoot or identify any problem. Any problem cannot go beyond these 5 steps. It looks very simple, but it takes a lot of patience, effort to go past each of these stages. Let's say, for example, you looked at the logs. You found out certain errors. You need to identify why there are errors, whether they are genuine or not so valid errors. Then you enable debug. Enabling debugging is a mess. Then you have to coordinate with the user, get the user to do your activity, capture the logs. You may not find anything in the logs. Then you take a thread dump. You load it to a log file, or you load it to summarize. You see what the thread is doing. You need the help of developer to identify what methods are getting executed by threads. If the methods have any problems, then you probably take a heap dump. You give it to the developer. The developer is not going to accept anything that there is a memory leak. So these are all time consuming activities, but these are the activities. For any troubleshooting, this is what you do. Even if you go to Oracle, this is what they do. Alright, now this is the troubleshooting methodology. This is the standard methodology. Any problem, same thing. It doesn't change. But as you move with troubleshooting, as you sort out more issues, you will get good at it. Anything, it's just like, anything, you practice it going on again and again and again, you tend to become good at it. So the same way, the troubleshooting also, you follow the same methodology. Even I follow the same methodology. But obviously there'll be slight difference between a 4 years guy doing this thing and a 10 years guy doing this thing. It comes with experience, but the method is same. So if you are at the beginning of WebLogic, if you are trying to troubleshoot, you follow the same methods a senior guy would follow. It will give you an edge. You will be able to learn it much faster. So this is the troubleshooting methodology. Alright, and it involves the same way we looked at a performance tuning also. In those areas, any problems, we will troubleshoot it using the same methodology. Now that's JVM. The next to the JVM, the next area that you will tune is the WebLogic server itself. If you go back to that stack that we talked about, this stack, we looked at JVM, the architecture of the JVM, how the compartment sizes changes should have impact, what is garbage collection, what are threads, dumps, heap dump, how do you analyze heap dump, all that stuff. Now the next area where you will tune probably is WebLogic server. Alright, then you have slightly JDBC and JMS. Alright, I think I'll stop it here, guys, for today. So it's getting too late for me and for you also. The next session, we can't have it tomorrow. There's a S4A class starting tomorrow. I am requesting you guys to wait till Saturday or Sunday. We're going to have an hour, 1 hour session to cover the remaining part. I don't want to hurry up these things. We want to go as slow as possible. So is it okay if we come back and meet on, let's say, Saturday? This is Sunday. Today is what, Monday? Yeah, today is Monday. So Saturday India time, which is Friday evening for you guys, especially those guys in UK and US. Is it okay? Chaudhary and Srinivas, you both. So I'm going to meet you again on your Friday time, which is Saturday morning for me. And in the meantime, I would also ask you to go through all the content that we did, videos. If you have any problems with the videos, let me know. So we'll fix those problems, and we'll also discuss about any questions that you might have. Alright, so I'm going to see you again on Saturday India time morning, same time. So till that time, make sure you go through it. One, performance tuning is really a very interesting topic, and the good thing is a lot of people think performance tuning is difficult to understand. It's not difficult to understand. It takes time to digest the concept. So just go through the video a couple of times. It's very nice. There are a lot of videos on YouTube. Go through some of those videos. You will really get really good at it. And performance tuning is, you really need to understand how WebLogic is working. So that's where you need to concentrate. And for those who are attending interviews or those who are planning to move on, this is the area where most of the questions come, especially the one that we talked today. People will ask you, what is garbage collection, why you need garbage collection, what are generations, what happens when garbage collection happens, how do you analyze a garbage collection log, What's a heap dump? What's a thread dump? How do you take a heap dump? How do you take a thread dump? These are the questions that get asked. They are all fundamental questions, guys. It's important that you have a very good idea of what they are. It's not about, yeah, I'll send you those questions, Pavitra. Yes, sure, I'll send you those questions. So it's not about the commands, it's about the concept. People are going to ask you why you want to change the compartment size. It's easy to say that you change the compartment size to improve the performance. The question is why you want to change the compartment size in the first place. So you should be able to tell the garbage collection requires certain time. And our assumption is the infant mortality rate is 80%. If it is not 80%, you need to give more time to the garbage collector so that it comes late, less frequently, so the compartment size is more, there will be more data. So the concept is important. And the infant mortality rate concept you won't find anywhere. That it took me a lot of time to identify and why you need to increase the compartment sizes. Everywhere you will see increase the compartment sizes, nobody tells you why. It's the infant mortality rate. That's a really important concept. Alright guys, so I hope you enjoyed this session. I want you to go through it one more time. Get really SOA, yes, same pin tomorrow, same this thing, same link, same time, everything same tomorrow. It starts. For those of you who want to join tomorrow, please join as usual at the same time, same meeting ID, everything same timing, same meeting ID, same URL, same everything same, and I am also same. Content will be different. Alright, so I'll see you tomorrow, those who are planning on joining. Otherwise, for WebLogic final session, I'll see you on Saturday morning India time, which is Friday for US and UK. Okay guys, thanks very much. It's been a very long session today. Please go through it one more time. Thanks very much.